tomorrow 2 homework assignments to me. Assignment number 81, problems 1 through 5. Okay, you did not do it in vain. And tonight's homework is to do assignment number 82, which I think is the first thing in the new problem set packet. Okay? If I haven't said it yet, please take out your calculator. You're going to need your calculator today. And for anybody who's interested, I'm staying for tutorials today from 1:15 until 2, let's call it 2:20. Because I need to head out and make it home to meet with the social worker and adoption and all the stuff. And no, probably mom, I'm not going to adopt you. All right. Yeah, better luck next year. All right. So here's where we are in the unit. We are unbelievably almost done with yet another unit in the calculus curriculum. We've learned all about Riemann sums and the 4 methods that Riemann has for approximating area. Those 4 methods are, Lewis? Trapezoid, that's one you're frozen. Right endpoint method, Carmen? Midpoint method, I thought you were going to go for the obvious one, Myra. The left endpoint method. And all 4 of those methods are ways to approximate this guy over here. Aaron, what is this?
The definite integral.
It's approximating the definite integral. And David, if I asked you, what is the definite integral? What is it giving you?
It's the area bounded by
Area bounded by 4 things, right? What are they? The function, the x-axis,
and the interval from A to B.
the interval from A to B. Then we looked at application problems. We looked at things like this guy here, the integral from A to B of v of t dt. And you guys all know that in a physics situation, if we're talking about velocity, the area under a velocity curve has to be... Oh, awkward. Displacement. So we've looked at the definite integral in terms of physics. We've also looked at the definite integral of, oh, maybe not the velocity function, but the speed function. And this one you guys know is total distance traveled. We've also looked at something called the FTC, the fundamental theorem of calculus. And the fundamental theorem of calculus says the value of a function at the end of the interval is equal to the value of the function at the start of the interval, plus the integral from a to b of f prime of x dx. The final value equals the initial value plus the total change. Everybody okay? All right, and then we had average value came to play. How do I find the average value of a function over a particular interval? Andrew, how did you find average value last time in all those homework problems?
By finding the definite integral.
Definite integral.
Then divided by well, okay, it's from A to B.
A to B.
F of x.
F of x.
Dx.
Dx.
Divided by B minus A.
Divided by b minus a. Everybody okay? All right, and last one. If, for example, we're doing some sort of an application problem, maybe we're even thinking about like that sand problem from the other day of the quiz. S of t was how fast sand was getting added into the pile at any particular time, and the definite integral represented how much. If your rate function, if you're integrating a rate function, the rate says how fast something's happening. And this guy over here is telling me how much has happened, how much was added, how much was taken away. Everybody okay?
Yeah.
All right, so for the next couple of days, I want to push your thinking a little bit more, and we're going to bring all of these ideas together. It's going to be very calculator active. So we've got this initial problem. I've got a swimming pool that originally contains 10,000 gallons of water. Water is being added into the pool at a rate of A of t gallons per minute, and at the same time, water is leaving the pool at a rate of L of t gallons per minute. So now we've got more things going on. We can study more complex situations. And I'm on page 46. So I've got some swimming pool. I am not an artist. We're not going to worry about this being accurate. But here's my swimming pool, and well, what do I know about this swimming pool? It initially contains 10,000 gallons. I know that water is getting added in at a rate of A of t, and for some reason, water is coming out at a rate of L of t. Everybody good situation? All right, take a couple of minutes. What I want to see what you can do is with these 6 problems, what I'm looking for is a setup. I'm not looking for a number answer. You don't have enough information to give me a number answer. But I want to know, how would you determine the amount of water that has been added to the pool during the first 10 minutes? We'll talk in a little bit.
Because it's asking my water has been added.
Even you're doing it.
Yeah. So you would divide it over 10.
Wait, what?
There is nothing in this problem that says you should be dividing. Right. The only time you can divide. There you go. Good. Right. All I'm looking for are setups here.
Oh, whoa. I don't know where I got it.
That's strike 2, buddy. One more strike this week and we're going back to 6th grade. Alright, amount of water added to the pool during the first 10 minutes. Most people seem to have integral from 0 to 10. A of t dt. Right, A is the rate, A is how fast. How fast did I add water into the pool? So when I integrate, this is going to tell me how much water was added into the pool in the first 10 minutes. All right, keep going. Trust those smarticle particles and read carefully.
During the 10th minute, so from 9 to 10.
Love it. Nice. You guys are pros. How much water leaks from the pool, right? So we get the water coming out during the first 15 minutes. Integral from 0 to 15. L of t dt. Amount of water that leaks from the pool during that 10th minute.
Just be 0 to t.
0 to t, 18.
Over et.
I thought it was just
equals.
Got it?
Thanks,
You
Paolo.
got it? I just thought it was why did you say
So you made me cut off for it? So you made me try.
Alright, just a quick show of hands. How many of you guys have these first 3 exactly? First one, integral from 0 to 10, A of t dt. Second one, integral from 0 to 15, L of t dt. Last one, integral from 9 to 10, L of t dt. Looks like just about everybody? Okay, so my easy question. How do you know whether you use the A of t or the L of t? David, how do you know?
Well, to compare, like, on the first one, it says being added.
Yeah.
And then on the second one, it says leaks.
Okay, so A of t means we're adding water in, and then this next one the water is leaking out of the pool. So you can handle multiple rate functions in a situation like this because we've got a good handle on the situation. All right, number 4, what time t will a total of 5,000 gallons of water have been added to the pool? At what time do I get 5,000 gallons in the pool? So first question, what function are we going to deal with? This has to be A of t. A of t is the rate that water is being added into the pool. I want to know how much, so hopefully we're all thinking integral. What I need is an equation that's going to tell me how much time passes before I hit 5,000 gallons. Now, Aaron, what are your thoughts?
0 to t.
0 to t.
Yes. Equals 5,000.
A of t dt, and we need for this to be equal to 5,000. Now, like we're trying to figure out not what is that final answer. We know what the final answer is. We're trying to figure out at what time do we stop now. And so the variable winds up in that like upper limit of integration. Are all the friends okay? Now I want to be really picky. We've had this conversation once or twice. I don't like that. College Board doesn't like the fact that you're using T as your limit of integration up here and your T in here, so do something. Right, if T, they're telling you T is the time when you reach 5,000 gallons, don't change this one. This T means something. Myra, are you okay? All right. So it's this guy here that you're going to change. Change it to whatever you want. A of x dx, A of s ds. It doesn't matter what variable you use. Don't use T. All right, now I'm really interested in this one. What's the total amount of water in the pool at the end of 1 hour? We'll talk in a little bit on this one. I haven't seen the right answer yet.
It'll be the definite interval of 0.
Be careful, reader.
Because it's an hour long.
You have to do the interval added minus the interval rate. Because you're taking apart both. That's the total. Yeah.
That's it.
All right. So conversations that I was just eavesdropping on. Total amount of water in the pool at the end of 1 hour. If I want to know how much is actually in the pool, I've got to consider everything that's happening in this situation. Meaning, I started off with 10,000 gallons. This is the initial value. What else happened?
Oh, yeah.
You've got water being added. How much water being added?
It's from 0 to 60.
It would be the integral from 0 to 60. Now, you guys are so darn good at this. Nobody seems to be messing this up. This idea of like the 1 hour, right? 1 hour, you guys know 1 hour is going to be 60 minutes. Because your rate function is being measured in gallons per minute, you have to convert over to minutes. So integral from 0 to 60 A of t dt, 10,000 that I started with, plus how much I added, minus how much actually is leaving from the pool, integral from 0 to 60 L of t dt. How many of you guys had that? Instincts are serving everybody well. Good. All right, last one. At what time t is the pool going to be empty? See what you can do.
What did you just set? This part?
Oh.
Would you have? Would you lose the 10,000?
When is that pool going to be empty?
It would be the same equation
This
except,
is the T, this is T.
and then you would probably change like the actual function, A of x and F of x.
But you just instead of 60, it's
Pool empty. I have 0 gallons. Alright, so I've got the 10,000 gallons that I started with, plus I've added a whole lot. Yeah, you guys don't like that.
No.
Alright, right, because we don't like the overusing the variable. Here's the thing though, we're talking about the same time. There's some magic time, we don't know what this magic time is, where I stop adding and I stop taking the water out. So we're going to change these variables here. A of x dx, and really it's irrelevant what you call it, it could be anything, but the pool's empty and that's the thing that I care about. Equals 0. Everybody feeling really good about this?
Yes.
Good. So we've got the setups under control. All I want to do is I want to push you guys now, and we're actually going to use the calculator. So Palomon, if you don't mind, I'm going to ask you to drive. If you guys flip over to page 47, I'll know you're there. Yeah, I would never wear shoes like that. That's right. All right, Palomon. So you guys can start getting this set up. And it's this one. Graphical functions.
That's what.
Yeah.
Yeah.
Yeah, it's the shoes that are wrong.
Yeah.
Kind of
I don't think the Photoshop picture is there at home. I think the shoes, you know.
Yeah, my head's not that boxy. Alright. So your friendly neighborhood mathematician comes by to evaluate the situation. Based on their advanced mathematical knowledge, they determine that water is leaking from the pool at the rate of L of t equals 3,000 over t plus 10 gallons per minute, and that water is being added to the pool at a rate of A of t equals 50 blah 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 gallons per minute for 0 less than or equal to t less than or equal to 60. Before the leak began, there were 10,000 gallons of water in the pool. Using this information, answer the questions that follow. So first bit of advice, graph these functions. You're going to need the graphs. You might have to mess around with this a little bit to get the right windows. Okay. All right, couple of bits of advice here. Bit of advice number one. If they give you a domain restriction, use that for your window. If these functions are only good from 0 to 60, only use them from 0 to 60. Make sure you can see the complete graph. Okay, nice. Palomone, are you going to fix the window?
No, I'm sorry.
Here. No, I'm not. All right, option 4. Window settings, option 1. And because the domain restriction is from 0 to 60, Palomone, we're going to go from 0 to 60. All right. So now we've got two functions. Now, if you haven't done it yet, I strongly recommend that you copy these functions down onto your paper so you can know what you're talking about. Not only do I want you to think about the functions, I want you to think about units. Units are going to come up in all these problems again and again and again. So on my x-axis, the x-axis is measuring, what are we measuring here?
Time.
This is time, and the units? The units for time are going to be minutes, not gallons per minute.
Oh, yeah.
On the y-axis, this is your rate, and this is going to be gallons per minute. Now, the College Board doesn't normally ask you to create the graph. They don't like scoring graphs. I'm not going to ask you to do that, but I think it's helpful, especially in those problems where you have two different functions. The red one, is that F2, Palomone?
It should be.
Yes.
It should be. Okay, so what's that second one? Is this adding or leaving?
The first one should be.
Adding. The second one should be adding. That's the
Wait.
one that you outlined should be adding. That
The
should
one
be-
that I outlined is adding?
Yes.
No.
So F1 is 3,000 over x plus 10. So that's the leaving. So L of t is leaving.
That's the red one.
And the red one, which unfortunately I've got a black marker for, is I'm adding water in there. And part A, the question is, determine the amount of water that has been added to the pool during the first 10 minutes. You guys know exactly what to do with this. Okay. Now here I want an actual answer, not just your setup. So how much water was added to the pool? We're going to do the integral from 0 to 10, A of t dt. And now that you've got the graphs set up, let's go over to the calculate screen so you can actually calculate what the value is. So it's menu.
So you see.
Okay, you're on on a calculator. No. No, no, no.
I didn't press anything.
Ay, Dios mío. If you could go back, there you go. Hit the escape button a couple of times. One more time. And then you're gonna go over to the, oh, I know what you did. You created the graphs on like that side of the screen on the scratch pad
Yeah.
versus over here. So what you need to do is add page, control add page, or control doc. Control doc, add calculator. And now on the calculator screen, to evaluate the integral from 0 to 10, menu, calculus, numerical integral, from 0 to 10, make sure you get the function right here. Right, it's the adding function, so which one is that?
F2.
Right, there's no need to retype all of this in, you've already typed it in once, and so is everybody okay that it's F2?
Yes.
Okay, now here's the thing, when you're, in terms of what you're gonna show me the function name, the proper function name. You're not gonna do this other thing of like F1 and F2, and what are we getting for numerical answer?
644.88.
Okay, Polymon's got 644.88. Polymon, can you do menu?
No, the next number is 0 anyways.
Yeah, but I need to see all three decimal places. Okay, you know what, I'll fix it on my calculator later. 644.880 is what Celeste says?
0390. If you want.
644.880 is fine, and the units
Yeah, we got Wait,
has to be,
that's not the answer though.
that's not the answer?
No.
Nearest gallon.
Ah, to the nearest gallon. So to the nearest gallon, your answer,
645.
645
Gallons.
gallons. Is everybody 100% okay with the calculator skills? All right, B, determine the total amount of water in the pool at the end of 1 hour. This is a 3-point question on a scoring rubric. I need to see your setup.
Oh, really?
I was making sure you knew.
That's not a problem. Okay. All right, 3-point problem. I see David's already on his way to 2 of the 3 points. 10,000 plus the integral from 0 to 60 a of t dt minus the integral from 0 to 60 L of t dt. And Andrew, when you've got a number answer, let me know what you got.
What about mine?
No, it's not. Well, you gotta do-
Palamon, are you gonna get us number answers? 10,000 plus your integral from 0 to 60 a of t dt minus the integral from 0 to 60 L of t dt. Giselle, do you have a number answer yet?
Yeah.
Do you get that as well? What do you get? 939. 10,218.939 gallons. Can I get some confirmation on this?
Yes.
Everybody good? Gallons. All right, has to be gallons. Now, here's the thing. I'd say this is a 3-point question if you use the initial condition, if you have both of those integrals, and then you get the right numerical answer. If you want to be clever and show off a little bit, I'm wondering if anybody could do this with 1 integral instead of 2. If there's some property of integrals that maybe could be used to make life better. Lewis, what do you say?
You can put the definite integral from 0 to 60 of a of t minus L of t dt.
So what I hear you saying is we want to do 10,000 plus the integral from 0 to 60 a of t minus L of t dt. Does that work?
Yes.
Right, you get that property of definite integrals that says I can take that definite integral and I can distribute it over subtraction. I can distribute it over addition. We've got all those properties we've played with in a little while. Everybody good? All right, C, create an integral equation that can be used to determine the amount of water in the pool at any time t. This is just going to be a setup kind of problem.
Oh, W T.
Right, so W is going to represent the amount of water in the pool.
All these figures.
The amount of water in the pool is going to be 10,000 plus an integral from 0 to t, a of something, d something, minus the integral from 0 to t, L of something, d, I guess, well, I went with x there. A of x dx, L of x dx. Everybody good?
C.
Good. Right, what I'm hoping is that this is a pretty comfortable experience. It's really important though, if your function is a function of t, then that t has to be used as your limits of integration, not in here in the integrand. All right, now for the real push. On what time intervals is w of t increasing? You're going to want to have a conversation with somebody near you about this. How would you figure out if w of t is increasing?
But I'm not sure it would cancel it.
What would have to happen for the amount of water in the pool to increase?
18 to be big.
If you take the derivative of an integral, then would that cancel it out?
Oh, that's it.
Having the graph in front of you might be helpful.
You're right. Good job, David.
Yeah, let's go back to the graph. So if the blue graph is the rate, it's how fast water is leaving, and the black graph is the rate, A of t is how fast water is going in. At this particular time, look here where I'm drawing my finger. Hold on. It escaped a couple of times. At this particular time right here, what happens to the water level? Increase or decrease at this particular time? Decrease because L of t is greater than A of t, but it's not how much water.
It's total amount.
It's not total amount. L of t and A of t are rate functions. You have to use the right word here. The right word here is how fast.
Oh, it's decreasing faster than it's increasing.
Yeah.
Right, water is decreasing here because L of t is greater than A of t. How about over here?
Still.
Over here?
That's when the change happens.
Right, where does the change happen?
Actually, at the intersection.
It's at the intersection point that you have the change that happens. Before, yeah, if you could just close out of that. Before you reach that point over here, you guys said we're going to be decreasing. So W of t is decreasing, and I would say because L of t, bless, is greater than A of t. Over here, you guys said we're increasing. Increasing? So like increasing forever?
Increasing on the interval, yes. On the rest of the interval, yes.
Increasing on the rest of the interval, because I think even over here at 0 and 60, they haven't crossed again, right?
Correct.
So over here, you're going to be W of t is increasing, and this is going to be because A of t is greater than L of t. So if the question in part D was on what time interval is W of t increasing, W of t is increasing when A of t is greater than L of t. So do we have an intersection point?
T equals
17.
17.685. But let's be careful. If you're saying increasing is where A of t is greater than L of t, then we're going to say 17.685 parentheses. Otherwise, they're exactly equal to each other. Until when? until 60 parentheses and
Brackets.
brackets.
Right.
At 60, what's happening? A of t is still greater. I know we're going fast. I'm going much faster than I would in an AD class right now. But all the friends are okay? All right, last question. This is the one I'm really interested in. During the first hour, when is the water level lowest? And what is that lowest water level?
And the
17.3.
Oh, the minimum of 8.
No, the beginning. In the
Well,
beginning.
it's just the minimum of WT.
Basically, when elevation larger.
You're doing the minimum of WT. Yeah.
If the water level is low, so I've heard from a couple of groups already, what we're really talking about is a minimum. What kind of a minimum, though? Not a relative minimum, an absolute minimum. So water level lowest means we're looking for absolute minimum. Absolute minimum for W of t. What's the candidate?
The endpoint 0 and 60.
0 and 60 for sure are the endpoints. We're going to consider those. There's one more.
The intersection.
The intersection point. The candidate is over here at the 17.685 because think about what happens with your water level. Your water level decreases and then it increases. So at 17.685, because W of t changes from decreasing to increasing, that's your candidate. You've got endpoints that you want to check. That's going to be t equals 0 and t equals 60. And just to like wrap this up, Miss Blakely at East End does an incredible job with this. She always has her kids build a table of values. On the left, they list the interval, the candidates, 0, 60, and I'm going to call this 17.685A. Right, so I'm going to like do a little store thing. And then what you want is, what's W at 0? How much water at time 0? 10,000. How much water at time 60? I think we did this work
Oh, wait,
already, right?
it's 10,218.
10,219 point something.
Yeah.
And then how much at time A? Well, that's going to be 10,000 plus the integral from 0 to A, little a of t dt, minus the integral from 0 to A, L of t dt, and whichever of these three is the smallest
Try to do it.
wins.
Yeah.
And you guys should know which one is going to be the smallest.
Probably A.
Probably 60.
Probably A.
I mean, they,
Probably A, has to be A.
Yes. It's change.
How many times does the function change?
Once.
Oh,
wow.
It happens once. So you actually could even skip this and just say there's only one change and it's at a relative minimum, so it must be an absolute minimum.
Nice.
Okay, tonight's homework is physics, lesson 82. Have a great day. Thanks for playing. 1 minute ago.